Hey guys, welcome back to day 16. We'll talk about the acid-base properties of salts. So my question starts with, what happens when a salt, and that's any ionic compound, dissolves in water? The first thing that happens is dissociation. And we'll use an example of potassium fluoride. So potassium fluoride, which would be a solid, would break apart into potassium ion and fluoride ion. The second part of when a salt dissolves in water, the second step would be solvation. And this is where these ions are surrounded by water. So our ions will have approximately 6 waters around each of them. And they'll be octahedral for these small ions. Potassium is positive, so the negative side of the water will be around the potassium. So we'll write it as H2O. You may even write it as OH2 to show you that oxygen is by the potassium. Conversely, fluoride, the positive side of water. So that would be the H, the O. So OH2 this way, H2O that way. That's how we would write it to show you what's going on. So this would be the inner solvation sphere, and then water, hydrogen bonds around to make a second solvation sphere and whatnot. But the first thing that happens is that this ionic compound will be dissociating, then be solvated by surrounded by water, and then maybe hydrolysis. So hydrolysis is a reaction with water to generate hydronium or hydroxide ions. And it happens when the salt is a salt of a weak base or weak acid. So we know salts which are ionic compounds, dissolve with almost complete dissociation. Provided that the solution is dilute and the salt is soluble. So the ions produced are solvated, or otherwise known as hydrated, by the water molecules. In some cases, the solvated ion may react with water in a process called hydrolysis. Again, this happens when the salt is a salt of a weak base or a weak acid. Now, I have my example up here. I have potassium and fluoride. We look at potassium and fluoride, KF, break them apart, K plus, F minus. Well, potassium, what does that? Is that a proton donor, proton acceptor? Is it a produced hydroxide? Where does it come from? What base would it come from? Well, potassium is a group 1 metal, and so potassium hydroxide, KOH. Fluoride. Well, it's not FOH, 2 minus, it would be HF. So we know that this is a strong base for potassium hydroxide, and we have a weak acid. So we draw that fluoride again. And it had its waters, octahedrally. Fluoride is a weak base. Since it's a weak base, it is in competition for the H+. So let's write that out. Bronsted-Lowry acids and base, acid base, is a competition for H+. And in this case, sometimes the fluoride gets the proton, because there's a Kb involved. So that means the reaction will be F minus, aqueous, plus water, going to HF and hydroxide. So hydrolysis is going to affect the pH of a solution. If you put in sodium fluoride, potassium fluoride, we're going to produce hydroxide in that solution and affect the pH. So how do I know what ions are going to hydrolyze and what ions are not? It's a great question. So we're going to have the no hydrolysis team. Group 1 metals, lithium, sodium, potassium, rubidium, and cesium. Of course, francium and radium, we're not going to play with radioactive ions. We're just not. Magnesium, calcium, strontium, barium. Those metals, group 1 and group 2. Now, I did not include beryllium, and I won't give you beryllium. Anions, you have chloride, bromide, iodide. You have nitrate. You have chlorate and perchlorate. Note, HSO4- is an acid. So therefore, it will not accept H+, but it will donate H+. So HSO4- is an acid. Polyprotic acids. So polyprotic acids have more than one dissociable proton, or more than one ionizable proton. So my example will be H2SO3, sulfurous acid. So we'll have two Ka values. We have H2SO3, aqueous, plus water, going to hydronium, and of course, hydrogen sulfide. And that Ka1 now equal to the concentration of H3O plus, HSO3 minus, H2SO3, and it happens to be 1.7 times 10 to the minus 2. Pretty decent size. Ka2, almost wrote A2 down, HSO3 minus, aqueous, and water, going to hydronium again, and sulfite. Ka2 equal to hydronium again, sulfite, and hydrogen sulfite. And that happens to be, in this case, 6.4 times 10 to the minus 8. Now I want to point something out here. Notice -2, -8. That's 10 to the 6 times different. So the first proton comes off many times, usually more easily than the second proton. Usually. Not always, but usually. So usually the first proton is always easier to remove than the second or the third. Let's write that down. The first proton is easier to remove over the second and third, etc. So it's always, the first is always easier than the second, then the third. So let's do an example. What's the pH? Of a 0.10 molar solution of H2SO3. Okay, well, let's look. And we got our K values right there. So back to Ka1, H2SO3, water, going to hydronium, and HSO3 minus hydrogen sulfite. Ice table. So I start with 0.10 molar acid, none and none of my products. Get a minus X, plus X, plus X. So at equilibrium, I have 0.10 minus X, X, and X. Ka1 from right there, there's our expression for Ka1 in blue here. And so 1.7 times 10 to the minus 2 equals X squared over 0.1 minus X. And hopefully we're getting really good at this now. And we understand that we can't approximate here, can we? Because that's -1, that's -2. It's 10 times different. We cannot approximate, so we actually have to do the math. So bring the bottom up, 1.7, and I'll write that out real quick. I have 1.7 times 10 to the minus 2, multiplied by 0.10 minus X equals X squared. Moving to the right. Distribute. I get 1.7 times 10 to the minus third minus 1.7 times 10 to the negative 2x equals x squared. Rearrange. 0 equals x squared plus 1.7 times 10 to the minus 2 minus 1.7 times 10 to the negative third. Hopefully we have your calculator all worked out, doing your quadratic formula. You get 2x values. We only care about the positive one of 0.034. So that's what x equals. So x equals hydronium in this case. However, there's a second step, isn't there? The purple one. So let's write out the purple one. HSO3 minus, this is Ka2, going to H3O plus and SO3 2 minus. Now, if we look up here, X represents hydronium and hydrogen sulfide. That means I'm starting with 0.034 molar and 0.034 molar, and of course 0 molar in our X table. Now, appropriately, you should probably use a different letter, like minus. I use Z because Z is easy, because sometimes my X's and sometimes my Y's, they can look very similar, and so I don't like to do that. I use Z, so X and Z. At equilibrium, I get 0.034 minus Z and 0.034 plus Z and Z. Ka2's expression, we go back up, is right there. 6.4 times 10 to the negative 8 equals 0.034 plus Z, I used orange, Z all over 0.034 minus Z. Can we approximate here? Well, I got negative 8 and negative 2. Yes, I can approximate. What can I approximate? I can approximate that Z to 0 and that Z to 0. So approximating, this is very similar to 6.4 times 10 to the minus 8 equals 0.034 times Z over 0.034. Well, I can just cancel the point all 3/4. So 6.4 times 10 to the minus 8 equals Z. So right there. So now, what is the concentration of hydronium? So the concentration of hydronium is equal to 0.034 plus X, which we solve for X, and then Z, 6.4 times 10 to the minus 8. So that means the concentration of my hydronium will be 0.034. That adds almost nothing. Now, does it add? Technically, yes, but it doesn't add anything. So from Ka1, pretty much our pH comes from Ka1. Ka2, and the reason it comes from Ka1 is Ka1 is so much bigger than Ka2. So the pH, of course, is negative log of hydronium, which is the negative log of 0.034, which is 1.5. And just to dive in this a little bit more, the concentration of sulfurous acid would be 0.1 minus X. So that would be, and I'll write it in blue here, 0.066 molar. X, 0.034 molar for hydronium. With bisulfite, same thing, 0.034 molar. 6.34. Z here, so sulfite is 6.4 times 10 to the negative 8 molar. And those are concentrations. That's the pH. So when you have these polyprotic questions, we're just looking at pretty much the first proton. Now, if there's 3, you got to look at the first and second. And it just depends on the size. So you can always do it out, and it won't hurt you. Let's talk metal ions real quick. So when we have a metal ion, like aluminum, in water. So if aluminum is an ion in water, it's solvated. So this would be solvated. We have more water around. What can happen here is that in this solvated ion that we have for aluminum is a small little ion here, Al3+, I have my waters. And oxygen is around, and it makes a coordinate covalent bond. So oxygen is giving all the electron density to the aluminum to, so to speak, bond there, to stay there, to interact. And oxygen doesn't like to share. It's a very electronegative atom. It brings electrons to itself. Aluminum is very positive, though, +3. So the electrons are very attracted to the aluminum as well, which means that these bonds can be weakened. So this bond can go to oxygen and H can leave. So what happens is that you get HAl, H2O, 5, OH, 2 plus aqueous plus H3O plus aqueous. Well, what kind of happened there? And so you actually have aluminum. If I draw another aluminum atom here, you have your 6 waters, or your 5 waters now. So let me put all those other ones on there. OH2, OH2, H2O, 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 same thing here. But what happens is we're left with O to H. That way. And then the H plus is floating around. So basically, we made an acid. So all metal ions, right, in our course, except group 1 and 2, are acidic in water. They actually produce H+. So all the metal ions can be acidic. Kind of neat. This leads us to the next question. Determine if the following salts will make an acidic, basic, or neutral aqueous solution. So we're going to make it acidic, basic, or neutral. A, potassium chloride. Will potassium chloride be acidic, basic, or neutral? Our ions, K plus, Cl minus. Are they on the no hydrolysis team? Yes. KOH, strong base, HCl, strong. So these are strong, and strong would be neutral. B, lithium fluoride. Well, I have lithium plus and F minus. Is lithium on the no hydrolysis team? Yes, it is. LiOH. That's strong. Fluoride is on the no hydrolysis team? No. HF is weak. Well, what is F minus? Is F minus a proton donor or a proton acceptor? Well, it's not a proton donor because it doesn't have a proton to donut, so it's going to be a proton acceptor, which is base. So this one would be basic. Let's do C. Last one. What about lead 2 nitrate? We got Pb, 2 plus, and NO3 minus. There's two of them, but NO3 minus. Well, NO3 minus is strong from HNO3. It's neutral, strong acid. Nitrate's on the no hydrolysis team. Lead. We have lead, and lead's a metal. And it's not on the no hydrolysis team. It's not on the no hydrolysis team, so it's going to be acidic because all these metals are acidic. Will sodium bicarbonate produce an acidic, basic, or neutral solution when dissolved in water? Well, what is sodium bicarbonate? NaHCO3. Of course, it separates right there. So we get Na plus, no hydrolysis. So, neutral. Bicarbonate, HCO3 minus. Well, what does bicarbonate do? Can it donate or can it lose? Can it donate a proton? Yes. Can it gain a proton? Yes. What happens? Ooh, wow. So let's do both. If I have HCO3 minus plus water, there's two options. We can get H2CO3 and OH minus, or I can have HCO3 plus water going to CO3 2 minus and hydronium. So I have basic or I could have acidic. Now, if we take a step back, baking soda, sodium bicarbonate, common name is baking soda. We know baking soda is a base. So we know blue is going to happen. We know that, vinegar baking soda reaction, we know baking soda is a base, it's going to accept a proton. We kind of knew that long before. Well, how are we going to quantify that? How am I going to prove that in this situation? Well, in purple here, I actually have Ka2. That's Ka2. Ka2. And Ka2 for carbonic acid is 5.6 times 10 to negative 11. So I have a number there. How do I get a number for bicarbonate being a base? Well, that would be a Kb. I have H2CO3. I'm leaving out state symbols for speed because there's a lot here. HCO3 minus plus H2H3O plus. And that's Ka1. Then we have HCO3 minus plus H2O carbonate plus H3O plus Ka2. Let's write their expressions. So Ka1 would be, of course, our H3O plus, HCO3 minus, and H2C, I missed the C, CO3. Ka2 is still hydronium, of course. CO3 2 minus carbonate all over bicarbonate. So knowing those two expressions for purple here, we got Ka2. That's what we have. That's the same reaction for Ka2. I wrote it the same way. For blue, this Kb happens to have H2CO3, hydroxide, and HCO3 minus. So we remember that, hopefully, Ka times Kb is Kw. But I have two Kas here, so which Ka do I have to use? Well, I have to use the ones with carbonic acid and bicarb. So I have to use carbonic acid and bicarb. So I have to use Ka1 in this situation because Ka times Kb has to equal Kw, which is just hydronium times hydroxide. I have to have them cancel. So in blue, this blue Kb is Kw over Ka1, which is 1.0 times 10 to the negative 14 divided by Ka1. And Ka1 for carbonic acids, 4.3 times 10 to the negative 7. You can always look that up in the book. Of course, use the book. So we get 2.3 times 10 to the minus 8. So now we're going to compare this number, 2.3 times 10 to the negative 8, to Ka2. Who's bigger? Well, that's much bigger, isn't it? That's 2, 5, that's negative 11, that's negative 8. It's 1,000 times bigger. And so we're going to be basic because of that. Because Kb is a bigger number, which means the base reaction goes further to completion than the acidic reaction. Kind of fun. Let's try another one. Will sodium bisulfite produce an acidic, basic, or neutral solution in water? Good question. Sodium bisulfate, NaHSO3. Well, we know that Na plus, no hydrolysis, which we're going to really like that in the next chapter. HSO3 minus. We know there is hydrolysis. Which avenue will it choose? Will it be, again, blue, HSO3 minus plus water to be a proton donor, or let's do proton acceptor first. That'd be H2SO3 plus OH minus. And that would be a KB. We also could have HSO3 minus as an acid. And that, of course, is Ka2. And Ka2 was 6.4 times 10 minus 8. I have to get Kb. Now, which Ka do I use to get Kb? Well, hopefully you recognize it's going to be Ka1, but let's show you. I have H2SO3, water, H3O plus, and HSO3 minus. There's Ka1, which is hydronium, HSO3 minus, H2SO3. So hopefully you can see already with Kb, that's what we're going to have. However, let's do the second one, HSO3 minus plus water, H3O plus, and SO3 2 minus. So Ka2, still hydronium, because it's Ka, SO3 2 minus, and HSO3 minus. So which species do we need? I need to have HSO3 minus and H2SO3, and it's this one. Because the Kb expression here would be equal to H2SO3 OH minus all over HSO3 minus. And so they're inverses. So Kb is Kw over Ka1, which is 1.0 times 10 to the negative 14. Ka1 was 1.7 times 10 to the negative 2. And so if I do that in my calculator real quick, negative 14 divided by 1.7 times 10 to the negative 2, I get 5.9 times 10 to the negative 13. Well, in this case, Ka2 is much larger, so this will be acidic. And that's the acid-base properties of salts. Take care, guys.